Hey guys, so we are about to place in the final piece of puzzle in our discussion of tensors. So far we got to know the history of tensor, how this entire mathematical concept of tensor came into our world. We saw that how it is helpful in comprehensively describing a load that you impose on a material and the response offered by the material. We also saw the easy way of writing these tensors, particularly when we express tensor as a matrix, how these entities can be easily represented, call those as Einstein's notation. And in the previous lecture, we saw the critical aspect of tensor, how we made tensor as a coordinate independent or independent of the frames of reference. Of course, it was not as straightforward as you might expect, but still that we were able to rather decouple the notations that are involved in describing a tensor from that of the coordinate system. So if there are i's and j's involved in describing a tensor, we were able to show that these i's and j's can be described without the use of any external frames of reference. Now in this lecture, so this is going to be the pinnacle of our discussion on tensor and hopefully the final lectures on tensor. So what essentially we would like to do is, having covered all this, the question now remains, so now what? And as part of these fishes here would respond, first of all, I didn't really think that we will come here. I thought the time would be so constrained and we would be discussing forever on those topics, but thankfully we are here. So I did not have anything planned beyond this, but still thankfully again we are here. So what we will now discuss is how we can use this tensor notation to describe the mechanical behavior of materials. So far we considered the aspects that contribute to the mechanical behavior, that is the load that you impose on a material and the response offered by the material. Now we want to combine both these together and then discuss the mechanical behavior using tensor. So we want to understand how tensor helps us understand describe the mechanical behavior in a comprehensive manner. Now, one of the easiest way, or rather expression that helps us or describes the mechanical behavior is written here. So this expression, of course, many of you might have come across. So this is what we essentially are doing here is we have something that causes the behavior of the material, and there is a response offered by the material. We are rather expressing them as a single equation. We have a causal agent, we have a response, we are bringing it as a single equation, and what we essentially observe in this expression here is the effect caused by the causal agent is rather linearly proportional. So here the causing agent is nothing but our stress, and the response offered by the material is strain. So there is a linear relation between the stress and the strain, and this is not even in the crystalline material, even in metals and alloys. This is not observed all through the mechanical behavior, or it is not observed in all ranges of stresses. So there is a specific range within which we are able to see this linear relation between the stresses and the strain, particularly in the crystalline material, and this region wherein we observe a linear relation between the stresses and strain, we call it as the elastic region. So my cause is directly proportional, is linearly proportional to my effect, and there is a proportionality constant that is involved. So this is we refer to as the Young's modulus. So of course we refer to this as Young's modulus or elastic modulus. I have to mention it again because down the lane in this lecture we will see some sort of an ambiguity in this, but we will get to that in a while. But as things stand now, we have an expression that describes both the mechanical condition that we impose on a material and the response offered by the material. So together we have an expression that talks about the mechanical behavior, or more specifically the elastic behavior of the material. Now we have already seen that the stress, when you want to express it comprehensively, we express it as a tensor, and correspondingly the effect that is caused by the stress, we express that as the strain. If our stress is in the form of a tensor, the strain that is caused by it, particularly in this linear region, can be treated as a tensor. So a comprehensive way of expressing this response offered by the material to the given stress assumes also a tensorial form. So we have stress that is expressed as a 2 cross 2 matrix, and we have strain that is expressed as 2 cross 2 matrix. If we could now go back to our initial discussion on the history of tensor, what essentially we did was, in that discussion, we attempted to relate two vectors. We attempted to relate a load, a vector, to that of an area, another vector. We wanted to relate load and the area. These two vectors, we wanted to relate. These vectors existed in their own spaces, and we wanted to relate these two. And when we related, that is when we arrived at a tensor. So there was a vector, and now we want to relate it to another vector, and when we try to relate it, we related these two vectors using a tensor. So this vector, mathematically we express this as a column matrix. So both these vectors, we express it as a column matrix, and the tensor that allowed us to relate these two vectors ultimately became the square matrix. So initially we had vectors represented as column matrix and we wanted to relate. It ultimately ended up having, or we were able to achieve such a relation through a square matrix, which we refer to as the tensor. So that is how we were able to relate or introduce the concept of tensor in this discussion, and also in this world we were able to relate or introduce the concept of tensor. Now if you take that understanding and place it in the equation that we have before us right now. So in the place of these column vectors, what we have now is a second order tensor. We are now relating rather two second order tensors. So one second order tensor is our stress, the other second rank or second order tensor is our strain. So we are relating these two second order tensors now as we related our column vectors. Now if you rather translate, or if you extend what we did in our previous discussion, in order to relate two column matrices, or in order to relate two vectors, we needed an entity that was a bit more exhaustive, mathematically exhaustive than that of the vectors, and that is how we got introduced to the tensor. So essentially speaking, we had two first order tensors, and in order to relate them, in order to bring them together, we introduced a second order tensor. Now if you take the same understanding and place it here, what we essentially have is, we have already two second order tensors or second rank tensors. Now in order to relate them, this E here, this Young's modulus here, has to assume a tensorial form that is at least greater than the second rank or second order. So if you take this understanding here, the way we introduce the tensor, and if you take the understanding and extend it to this expression here, without getting into the specifics of it, based on that foundation alone, we will be able to say that the E, the Young's modulus that relates the second order stress to that of the second order strain, should at least have an order that is greater than second. Now this brings in a huge problem for us, primarily because when we are writing something down on a piece of paper, like in this virtual piece of paper, it is possible for us to easily describe a second order tensor, because second order tensor is nothing but a matrix. So irrespective of the dimensions I take, I will be able to express it on a piece of paper. So still it's a second order tensor, and I have absolutely no problem in expanding it. Rather, please pardon me, it should be N1. So there is absolutely no problem in expressing this on a piece of paper. Now if I go beyond the second order tensor, what it essentially means is, if let's say I want to express a third order tensor or third rank tensor, so generally I could refer to it as I, J and K. So if I want to express it on a piece of paper, I will be able to express my I and J component. I will be able to vary my I, J component. But if I want to introduce my K component, then I have to add a third dimension that pops out of my paper. So it means that when I want to write this third order tensor down, it becomes impossible for me to write it on a piece of paper. So essentially it means I won't be able to express this equation if I want to on a piece of paper. So originally I related two vectors, I related them using a tensor. Now I want to relate two second order tensors. So it means the entity that's going to relate these two needs to have an order that is at least greater than 2. So let's assume, if at all I assume that it's just a third order one, of course it's a fourth order, but still if I assume that it's a third order one, then it means that even if it is third order, I won't be able to express it in the piece of paper, because I need to have a third dimension. So all that I'm writing is, when I'm using a second order tensor, all that I'm doing is these 1, 1, 1, 1, 2, they contribute to my I and J. So if I want to introduce my K, it has to pop out of the paper, which I won't be able to do so. So essentially then, writing this expression here, which accommodates a fourth order tensor, I, J, K, L, a fourth order tensor, in the form of my Young's modulus becomes absolutely impossible. Even though I'm able to conceive a 3-dimension, even positing a 4th dimension is, at least for me, is not possible. And having something written down in the 4th dimension, at least as things stand, becomes extremely difficult. So my goal was to use my understanding of tensor to describe mechanical behavior. At the first instant, I'm choosing something that is easier for me. That is, I'm choosing a linear relation between a stress tensor and a strain tensor. Just there's a linear relation. I want to express it using the tensor understanding or tensor notations I have learned. At the first instance, I face something this hard, because when I'm relating two tensors, I need a higher order tensor, and writing an higher order tensor is proving to be difficult for me. So this is where we stand. Even when I want to describe something as easy as the elastic relation, I face a problem in using tensor notation to express them. So this is where we have a Voigt notation come into play, which helps us in describing this elastic behavior using tensor notation without compromising any of the components of the tensor notation in the form of what we are familiar with, in the form of vector notation, in the form of column matrix and the square matrix. So we introduce this Voigt notation, or the Voigt notation essentially allows us to describe this expression here using a vector notation, but still on a piece of paper. If I want to write this as it is, it becomes impossible task for me. But if I use Voigt notation, it allows me to express this equation here on a piece of paper. The way it allows me to do is, this is a square matrix, this is a square matrix. If I treat them as square matrix, then I have to come up with a 4-dimensional Young's modulus. So what Voigt notation helps us to do is, this Voigt notation helps me to change this two square matrices into column matrices. It essentially, so to speak, converts the vector notation into, or rather a tensor notation, second order tensor notation into a vector. So by doing so, it allows me to treat my Young's modulus as a square matrix. So that is what Voigt notation allows me to do. So essentially, even though Einstein notation helps me express these entities in an easier way, it's Voigt notation that helps me in describing or writing this mathematical behavior or this mechanical behavior on a piece of paper, because it translates the tensor representation of the stress and strain into a column matrix. Now, before changing this tensor notation of stress and strain into column matrix, let us consider this way of expressing the matrix. So this way of expressing the matrix, it indicates that the matrix that I have is a symmetric matrix. Of course, this being an undergrad course, and not many of you should have, many of you should have seen several theoretical papers. So essentially, when you see a matrix that is as incomplete as this, what it essentially means is this is one way of expressing the symmetry of the matrix. So what you observe is a symmetric matrix, and these terms. So your sigma 1 2 is equal to that of sigma 2 1, sigma 1 3 is equal to that of sigma 3 1. So essentially what is happening here is, so these are what we refer to as the shear stresses, and the shear stresses are the components of the shear stresses, or the shear stresses are equal in magnitude. So therefore the stress matrix that you get is symmetric in nature. So therefore you can express it by just using 1/2 of your matrix. So that is exactly how we have represented it. So if this is left blank, it doesn't mean that this assumes a value of 0. Of course, this might be trivial to many, but still. So when you express a matrix like this, there are many papers wherein the symmetric matrix is expressed in this way. So I just want to expose you to this way of representing the symmetric matrix. So now let's consider how we can write this into a column matrix or a column vector, so that it becomes easy for us to express this relation here that describes the elastic behavior of the material. Now the way you express the stress tensor as a column matrix is something like this. So what essentially we are doing is, we are first considering all the diagonal terms, the significance of which is these are the stress that are acting in the normal direction. These are the normal stresses, and once we have covered all the normal stresses, then we take this path here and include all the shear components of the stresses. So the components of the stresses, the 9 components, we categorize into normal and shear components. So the first, when we want to translate this into a column matrix, we first include all the normal components. So here goes all the normal components, and then we take this pathway, this one, this one, and this one, to encompass the shear components. Now of course, since we have written this in the form of column matrix, we no longer need two indices for us. So it can be expressed as something like this. So we have now, this is what we refer to as the Voigt notation. And what we essentially have done is we have translated the square matrix into a column matrix. Or in other words, we have expressed our stress tensor into a vector. And because now we have expressed it in the form of vector, instead of two indices, we just have to use just one index here. Now it is vital to note that there is a specific pathway that we took. We initially covered all the normal stresses, and then we covered the shear stresses, and the pathway we took is something like this. So this is how we were able to translate our tensor or stress tensor to that of the column matrix of tensor. Of course, the same can be adopted for our strain, because the way we express stress and strain are of the same form. Strain is also a square matrix. So this also equivalently can be translated using the same pathways that we took for our stress. So now once we have converted our square matrix or the second order tensor representation of our stresses and strain into a column matrix or a vector representation, it becomes possible for us to express this entire elastic behavior of material into something like this. So what we now essentially have done is we are in a position to write this elastic behavior into this form here. So once we are able to express the tensor into a column matrix or a vector, the corresponding tensor that relates these two column matrices becomes a square matrix of the dimension 6 cross 6, because there are 6 entries in each of these tensor. Now, just to make you understand what this means and how we can relate it to our crystalline materials, so I just introduce this representation here. So again, these indicate the normal stresses. So as you can see, 3, 3, 1, 1, 2, 2, these are our normal stresses, and these 3 here indicate the shear stresses. Now, when I want to describe the effect of this component of stress, when I want to describe the effect of this component of stress, all I need to do is multiply this row to that of this column. So let me repeat, if I want to describe the effect of this component of stress, I'm imposing a load, I'm resolving it into components, and the component that I'm considering is a normal component. I want to understand the effect of the normal component, that is the strain caused by this normal component here. So if I want to do that, I just have to multiply this row with that of this column here. And by the way, guys, this is referred to as, for some reason, stiffness matrix. So this is referred to as stiffness matrix. Some of you might be able to sense some ambiguity here, but still this is referred to as stiffness matrix. There is one other question we need to address here, that is, why is there a 2? When my stress is just 1, there is no prefactor here. Why is there a 2 prefactor here? So again, there is a reason why I called this as a cause and this as an effect. It might sound philosophical, but this was not my intent. So I call this as cause and this as an effect, because when I consider the shear components, we find that these two shear components, that is the causal agents, the magnitude of them are equal. Even though these are one shear components, that is sigma 2,3 and sigma 3,2, they are balancing shear components. There are two different strains that are introduced by this one causal agent here. So there are two distinct, even though their magnitude is equal, these are two distinct shear strains that are caused by one shear component. So this one shear component causes two effects, and both these effects, even though their magnitude are same, they act in different plane and they act in the opposite plane in the opposite direction. So in order to encompass these two, we have a prefactor 2 here. Alright, so we have now expressed the elastic behavior using Voigt notation. The Voigt notation translates the vector representation of my stress and strain to that of a column matrix. So that allows us to express my stiffness matrix not in 4 dimension but in 2 dimension. Now, if I want to understand the effect of this normal stress, all I have to do is multiply each of these components to these components here. Then I'll be able to understand what is the effect of this normal stress here. Now, it is vital to note that this normal stress sigma 11, this normal stress acting in this direction, it is causing an effect in the same direction and also in this direction and in this direction, meaning the load that I'm imposing in this direction has an effect in this direction and in this direction. So if I have a cube of a material here, I'm able to understand the load that I'm imposing in this direction has an effect of this direction and in this direction. Why should a material have an effect in the perpendicular direction? Now, if you consider, particularly in the elastic region, if this is my sample and if I'm stretching it, I see my sample, the dimension of my sample getting reduced in the perpendicular direction. In this direction it will get reduced and in this direction it will get reduced. So this is what we refer to as the Poisson's effect. So it means it is possible for me to conceive that these strains are valid, meaning I have a load, a normal load in a specific direction, and it is causing an effect in the perpendicular direction. I can conceive that. But how will I be able to understand there is a shear components of strain? How will it make sense to me that a normal load that I am imposing is going to cause a shear component of strain as in this and this? How is it possible? Because if it has to cause a shear component of strain, when I resolve this load onto these directions and plane, it should be a non-positive load. But if I resolve this, these are like now perpendicular. If I resolve this, if these are 90 degrees, if I resolve this, I understand that there is no load acting in this direction when the only load that I am imposing is this. The sigma 11 is acting in this direction. If I want to resolve it in these two directions, there won't be any load or any stress that is acting. So correspondingly, there is not going to be any strain, because if I resolve it using cos theta, cos 90 is 0, so there will be net no stress acting in this direction. Then how or from where can I get these stresses? How can these stresses be non-zero? Or how can these strains be non-zero? So that is what we need to, or what this matrix here describes. So I'm imposing a load in the normal direction, but I see that this normal load is kind of introducing shear stresses and correspondingly the shear strain. How is it possible? As long as the crystallographic axis that I'm considering are perpendicular to one another, this is not possible. All these will turn to zero. But on the other hand, if these thetas that I'm considering is not equal to 90 degrees, then in such a cases, I will be able to resolve my normal stresses to also the shear stresses that act on the plane. So if I have a crystal system wherein the crystallographic angle of the system is not orthogonal, it's not 90 degrees, then it becomes possible for me to have shear components of stresses even though all that I'm imposing is the normal load. So only in those cases, this makes an absolute sense. So I want to understand the effect of a normal stress. The effect of the normal stress includes both normal strain and shear strain. Normal strains I'm able to understand because Poisson's effect gives me normal strain, but the reason I'm able to observe shear strain is primarily because my crystallographic angles are not 90 degrees, they are inclined. So now I'm able to resolve my normal stress to some shear stress, and I'm able to correspondingly to come up with a strain. So what then this matrix here tells me is that this matrix here, it talks about the anisotropy of the crystal system that I'm considering. So beyond describing the elastic behavior, is now talks about the property, the behavior of the property of the material, the nature of the material. So this is valid only when I have such a system. So only when I have a triclinic system wherein the crystallographic, all the three crystallographic angles are not 90 degrees. If I have three crystallographic angles and all of them are not equal to 90 degrees, then it corresponds to triclinic crystalline structure. In triclinic crystalline structure, even if I impose a normal load, I'm going to experience shear load and corresponding shear strain. This is exclusively possible in case of the triclinic structure. So this understanding I will be able to gain by just looking at this mathematical description. If I just consider this, it won't give me much of an idea. But if I consider the expanded form of it, this tensorial representation of my elastic behavior helps me to understand what sort of a material it is. So I'm considering a completely anisotropic material. So what I mean by anisotropic material is, depending on the direction I'm choosing, the response I get from my material is different. So this is my cause, again my stress is my cause, and this epsilon, the strain, is my effect. So depending on which direction I choose, this direction and this direction, depending on which plane and direction I choose, the effect is going to be different. And that is what we mean by anisotropy. And the most anisotropic case is when all the entries are non-zero. So when I have all these entries as non-zero, it means even my normal load is going to give me shear strain. And this is possible only when I have my crystallographic angles not equal to 90 degree. That is my triclinic structure. So we have a huge advantage in expressing a simple mechanical behavior using a tensor notation like this, because this helps me understand what sort of material I'm dealing with. So when I'm dealing with highly anisotropic material like triclinic material here, which is going to give me a shear strain, even though I'm imposing a purely normal stress, the way it achieves it is in this form here. And this helps me, this representation here tells me that this material that you are dealing with is as a crystallographic angle that is not perpendicular or not 90 degrees. And ultimately, I'm able to narrow down what sort of a crystal structure is this. So with this understanding, how the tensorial representation of the mechanical behavior helps us gain more information out of the material, with this foundational understanding, I will wind up this session. The next session possibly will be even more smaller one, because we will try to build on it. I already have crossed my time now. I usually want to have the structures a bit palatable. So what I'll do is, we will build on this, and then we will understand how much further we can learn from this tensorial representation of the mechanical behavior. See you in a minute, guys. Bye.